Living in the future, huh? Feels that way sometimes, right? And with all the talk about deep learning lately, it's no wonder. So today we're doing a deep dive, getting into the nitty-gritty of it all with this paper.
And not just any paper, we're tackling deep learning from 2015.
Co-authored by LeCun, one of the heavyweights in the field. This paper's huge E, a real roadmap for understanding, well, everything from how algorithms seem to know what you want to buy online to maybe even the future of AI.
It's got that much impact.
Right off the bat, they hit you with this idea of deep learning being like representation learning. Honestly, sounded a bit jargony to me at first.
Sure.
What's the breakdown in plain English?
Okay, so picture this. You're trying to explain to a computer what a cat looks like.
Good luck with that. All they see are pixels.
Exactly, just a grid of numbers. Colors, brightness, that's all. Representation learning, especially deep learning, it's about getting the computer to go past those pixels.
To understand somehow.
In a way, they build their own understanding of what that data represents. Like it's learning its own language to make sense of it all.
So instead of saying, hey, look for pointy ears and whiskers.
It figures out those defining features itself.
Wild.
That's the heart of it, recognizing patterns in the data, building its own cat representation.
Okay, but they call it deep learning. Why deep?
Layers, my friend. Think of it like filters,
Yeah.
each one refining how the computer sees the data.
Okay.
So you start with those raw pixels, right? First layer might just be picking up edges, lines, basic stuff.
Simple.
But then, next T-layer, it takes those edges and starts forming shapes. And this keeps going, each layer building on the one before. More and more complex, abstract information.
So it's like pixels.
Okay.
Edges. Gotcha. Shapes. Wait a minute. That's a paw. That's fur. That's a sea cat.
Nailed it. That's how they tackle these huge GE tasks.
Yeah.
And not just images. We're talking language processing, even predicting how proteins fold up.
No kidding.
And you know what? You're probably using this tech every day without realizing it.
Really?
Oh, yeah. Movie recommendations, spam filters, even how your phone understands what you're saying. Deep learning's probably behind it.
All right, so deep learning, it's everywhere, it's powerful,
Mhm.
but how does it actually learn? What's the secret sauce that makes these machines so smart?
Well, the paper dives into this really cool concept called supervised learning. It's basically how we teach these deep learning models.
AI school, huh?
Uh-huh. Yeah, kind of. Imagine you're teaching a dog a new trick. You demonstrate, give commands, maybe a treat when they get close.
And eventually, hopefully, they get it.
Exactly. Supervised learning is kind of similar. We train these models by giving them tons of data. But here's the key. It's labeled data.
Labeled how?
So say we want to teach a model to recognize flowers. We show it thousands of pictures, right? But each one is tagged. Rose, tulip, sunflower. You get it.
So the model's looking at all these pictures, trying to find what links the image to the label. Like, okay, these round shapes with petals, those are usually tagged rows.
Precisely. It's all about pattern recognition on a massive scale. And then there's this process called backpropagation. That's how the model learns from its mistakes, gets better over time.
Backpropagation. Sounds intense.
It's actually quite elegant when you break it down. Imagine throwing darts. First one might be way off, right? But you use that feedback. How far off were you? Which direction?
Adjust your aim for the next throw.
Boom. Backpropagation. The model makes a prediction. If it's wrong, it calculates the error, sends that information back through the network.
And adjusts something.
Think of it like fine-tuning, like knobs on an old radio. Those knobs are the parameters controlling how each layer interprets the data.
So backpropagation is like, whoops, missed the mark. Better adjust those knobs.
And with each adjustment, the model gets better at predicting, like a student reviewing the wrong answers. Now, what's fascinating is for a long time, people thought this wouldn't work with really deep networks.
Oh, too
They
complicated.
thought the models would get stuck, couldn't find the optimal solutions, but thankfully, wrong.
So they figure it out.
LeCun's paper explains how these deep networks are surprisingly good at navigating that complex data landscape. They find solutions, even if they're not perfect at first. This breakthrough, it's opened doors. Not just image recognition, but like you said earlier, drug discovery, understanding proteins.
All because these algorithms can spot patterns WB can't.
Exactly. Now, speaking of breakthroughs, there's one type of deep learning architecture. They really highlight convolutional neural networks. Condom nets for friends.
Condets, right. Aren't those big for image stuff?
The superstars of image analysis, and they're modeled after how our own visual system works. They break images down into smaller chunks.
So instead of looking at the whole picture at once,
It's like, okay, that's ear, a tail, fur.
analyzing it piece by piece.
And as it moves through those layers, it combines those smaller details. Edges and lines become patterns, eyes, noses, eventually a whole face.
And because it's learned those features, it can recognize a dog in any picture. Doesn't matter the breed, the pose.
Generalization. That's a big part of what makes deep learning so powerful.
Okay, so comments have the image thing down, but language, that's got to be way more complex, right? How does deep learning deal with something as nuanced as how we communicate?
Now that's where it gets really interesting. One of the big breakthroughs here is distributed representations.
Yeah.
Might sound kind of technical,
It does.
but it's actually pretty intuitive. See, normally a computer sees a word, it's just a bunch of ones and zeros. No meaning there.
Just a symbol.
Right. But with deep learning, we can turn those symbols into something much richer. We're talking vectors. Basically lists of numbers that capture meaning.
So instead of just king being a random word.
It becomes connected to queen, royalty, even power.
Huh.
Words with similar meanings, their vectors are closer together in this big multi-dimensional space. So king is closer to queen than, say, penguin.
It's like a map of language where the word tells you what it means, how it relates to other words.
Exactly. And this changes everything for things like translation, instead of rigid rules.
Which never worked that well.
Now we've got algorithms that actually get nuance, accuracy, all because they're tapping into the underlying meaning.
So no more robotic translations?
Getting better all the time. Now, when you're talking about sequences of info, like words in a sentence, notes in music, that's where RNNs come in. Recurrent neural networks.
RNNs, right. They're the ones that deal with stuff that happens over time, right?
Exactly. What sets them apart is memory. They remember previous inputs, so they understand context.
Oh, so it's not just hearing one word. It's getting the whole sentence.
Big difference. And this memory is huge E for translation, speech recognition, even predicting the stock market.
Now, the paper mentions LSTMs, too. Long short-term memory. What's that all about?
Ah, LSTMs. They're a special breed. See, regular RNNs, they have a bit of a short-term memory problem.
Like me trying to remember what I had for breakfast yesterday. Forget it.
Exactly. LSTMs, they were designed to fix that. They have these special memory cells, can store info for way longer, handle those complex long sequences.
Supercharged memory. What do they use for?
Oh, all sorts. Those super accurate voice assistants we use, chatbots that sound more human, even composing music, writing poetry that's hard to tell apart from human-made stuff.
So with all this in mind, what's next for deep learning? Where's it all going?
Honestly, the future is wide open. LeCun's paper hints at some pretty wild possibilities, especially with unsupervised learning.
Unsupervised. So no more labeled data.
Exactly. We take the training wheels off, give the model data, let IT figure out the patterns, the connections.
Like giving a kid a box of Legos with no instructions and seeing what they build.
Perfect analogy. Unsupervised learning could be huge EE. Medicine, art, scientific discoveries. Imagine machines finding things in data that would take us lifetimes.
That's both incredibly exciting and a little intimidating. Like we're on the edge of something huge.
We are. And as we explore these possibilities, we have to think about the ethics too, making sure these powerful technologies are used responsibly.
Absolutely. Well, this deep dive has been mind-blowing. From the basics to the future, deep learning is full of surprises.
It's been a pleasure joining you today.
And to all our listeners, if you want to go even deeper, check out the full paper by LeCun, Bengio, and Hinton. It's essential reading for anyone who wants to understand where technology might be taking us. For now, keep those brains buzzing, and we'll catch you on the next deep dive.